Hi, everyone, and welcome back to part 6 of our Block 74 Apollo Guidance Computer series. Today we're going to be talking about the Q register. So we'll go into our diagram of the central processor of the AGC, and we previously talked about the Z register here, as well as the B/C register down here. So the Q register, like the Z register, is part of the one of the special and central registers within the Apollo guidance computer. Now, these are registers that can be accessed in one of two ways. They can be accessed through control pulses. So we have our write Q or WQ control pulse here that basically writes in data from the write bus or the WL lines, stores it into the Q register, and then we've got an RQ or read Q control pulse that reads data out onto the bus. Now, these registers can also be accessed as if they're memory. So in this case, the Q service is mapped to octal 0002, so address 2. So it can be accessed as both a kind of a memory address or as a register. Now, there's one other element, the special feature of the Q register, is that it also provides in and out access to the I/O or channel bus. So if you notice here, we've got this in-out channel word line here that's associated with our kind of write amplifiers and various buses. So the Q register acts as a kind of a place where we can bring in data from the I/O bus, which is separate from the write line or internal data bus, and push data out onto the I/O bus. And this I/O bus is how the guidance computer interacts with the outside world. So there, and we'll talk about this in some later sessions, but there are a number of I/O or channel registers that store various bits of data or bring bits of data into the computer. So this could be anything from the display and keyboard interface, or the DISCI, which is the primary method that the astronauts use to work with the Apollo guidance computer. Um, anytime you punch a keyboard or punch a key in, that'll actually send data to the or it'll put data into one of the channel registers, and then the computer can then access those channel registers to bring that data into the central processor. And likewise, it can push data out into those channel registers in order to display numbers on the keyboard, for example. And this is how all of the I/O and integration with the spacecraft works. So things from information from gyros, guidance platforms, RCS thrusters, hand controllers, etc., all kind of flow through this in-out channel word and the channel registers, which are external to kind of this central process control section of the Apollo guidance computer. So let's look at the kind of the details from the manual itself on the Q register. So the Q register is primarily used for instructions relating to the TC or transfer control instruction. So this is where the return address is stored for subroutines, interrupts, cases where the computer has to go off and kind of interrupt whatever it's doing, go off and do something else, and then come back and kind of recover what it was doing before. So this is, based on some of the instructions, during Q exchange, the value in Q is exchanged with the quantity in the memory. And we've got a couple of control pulses that kind of manage how data comes in to our register and how data comes out. So as normal, we've got our write timer, and then we have our WQ or the Q register write enable. For data going out, we have our read timer and then our RQ, which is the Q register read enable. And then we have our XB2. So this is our signal we get when our memory address, which is our stored in our S register, is 0002. And we also have our signal that either WSC, which means that we want to write into our register as an addressable register, or RSC, if we want to read from that memory address or register as a memory address. We also have a few other signals to the WCH and RCH, which is to kind of manage data in and out on the I/O bus. And we use the same XB2 memory address in order to signify which register we're going to be writing in and out of, because the L register also uses the channel bus to write data in and out. And then we've got our write lines for our internal data bus, and then our CH or channel, which is our I/O or external bus. So if we look at kind of the logic gates and kind of how things are structured, we've got this a series of data that's used in order to determine when do we assert our write to our registers or clear our registers or read from our registers. So let's actually switch over to the schematic and kind of how we've laid it out. If we look at the kind of the input logic here, very similar to the RZ. So we've got our RQ, or sort of or similar to our Z register. So we've got our RQ, which is one of our kind of paths that we can use to write data into our register. We have our addressable, so XB2 and WSC signal, which is another path that we can use to write data into our register. And then we have our channel. So we kind of have this, again, address 2 along with the WCH signal in order to write data into our bus. Now you notice here, and this is where these videos are actually helpful for myself as well. I actually recorded this video earlier and realized as I was explaining it that I had made an error with some of the layout. So I had to make a few changes, and as a result, this would normally just be a 2-input NOR gate, but because I had originally wired it up as a 3-input to include an additional control signal that we do not require, I'm just going to use that, tie that to ground, so it essentially acts as a 2-input NOR gate. You can kind of see that here and here. Now, one thing that we do differently on the right side is, we've got our signal, so our chip enable, which allows us to write data into our D registers, which are right here. But we also need to select where are we going to get data from in order to write into our Q register. So most of the time, this is going to come in from our write line, so WL1, WL2, 3, and so forth. But if we're kind of asserting the WCH signal, which means that we actually pull it down and go 0 to assert that we want to do or basically write from the channel bus. So we invert that so we can get that to our select signal. In that case, we have, if this goes low, which means it's been asserted, we have a 1 on our select bit. And that means that we will pick our CH01, CH02, CH03, or CH04, and so on. Now we could have just flipped this around and avoided using this this inverter, but we had the extra inverter on the board, so I just kind of used it this way rather than flipping around all of the this could have been CH1 and WL1, and then we could have avoided using this inverter if we wanted. The right side is fairly similar, but because we have 2 buses that we're writing out onto, we kind of split the control signals out 2 ways. So we have this kind of top layer here, which is with our write timer. So we can, when we have the write timer pulse, that's going to be incorporated into our logic to determine when we push data out onto the bus. And we have our RQ scenario, and then we have our RSC connected to our XB2. So if we're using it as an addressable register, we've kind of got these scenarios which we combine in order to provide our chip enable for our, you can see here's our octal transceivers that push data out onto the write bus. And this is where our chip enable is connected to enable this to push the data in the Q register out onto the bus. Now we also have the scenario where we need to push data out onto the channel, the IO channel bus. So this is where we have this signal asserted, also with the XB2 address, and then the write timer as well. And that just kind of flows to the second set of octal transceivers, which are connected to the channel bus. And that allows us to push data out onto the I/O channel rather than the write lines. So that's the kind of the layout, and we've created a little bit of a simulation here to kind of show how it will work. So we have kind of on our right side, see if we go 0, so we assert our WQ. The logic allows us to, on the chip enable side, for those D registers, which is also logic low, that'll enable it to write. We also have a case of if we have XB2 and the WSC signal, that'll also allow us to write. And then we also have the scenario here with the I/O channel also associated with XB2 to write that data into the register. On the read side, we kind of have the two scenarios, which is one is just our read the data out onto the write bus, and then we have the read the data out onto the channel bus. So we have a scenario here where we've got RQ is asserted, and then we pulse our write timer. The read timer, that's just tied to the clock inputs on the D register, so it's kind of connected directly. Whereas on the write timer, we incorporate that logic into the chip enable for the output bus transceivers. So we can see here when we click the write timer, we're going to enable our write out onto the bus. And we also have our scenario where it's addressable, which means we've got our RSC plus our XB2 address. And so we have that scenario here. We can see that's enabling that. And then we also have our scenario where if it's a to the I/O channel, we've got our scenario here where we're pulsing that out, sorry, XB2, and then RQH to pulse that out to the channel bus. Now, what does that look like from a bill of materials? So we've got kind of here's the Q register as it's been built. And so we've got four 74LS173s. That's the register itself to store our 16 bits. We've got our 4 octal bus transceivers, 2 for the write line bus and 2 for the channel bus. And then we have 4 74LS157s. This is our quad 2-line to 1-line selector. This is where we use it to select our input, whether it's coming from the channel bus or the write line bus. And then associated logic, we've got the 174 LS04 hex inverter, inverter, not core. The 174 LS02 quad 2-input NOR gate, 274 LS27s tri 3-input NOR gates, and then the buffer that we've used on the other boards as well, just for our clock and reset. Associated components, we've got our 16 red LEDs to show our contents of the Q register, along with their basically current resistors so that we don't sink too much current. And then we've got our 0.1 microfarad ceramic capacitors for each chip, just to, again, make sure its power supply is nice and happy. And then we've got our 96-pin connector that we use to connect to our backplane. Now, the Q register is probably the last one of the, I guess, simpler registers. The Z, the B/C, and Q are the easier ones. The other registers start getting a bit more complicated. So before we wrap today, I'm just going to quickly show a section in the documentation, which is going to start becoming a bit more important as we go through a variety of the different registers. So this describes all of the control pulses generated within the Apollo guidance computer. Now, some of them we've already talked about. If we go down the list, we can see that there is our our RC. This is our read, so read data out onto the write lines from the C register. We've got our RB. Today we talked about our RQ, which is read bit 16 through 1 of register Q onto the write lines. And then we have our RZ that we talked about. But there are a number of other control pulses that are tied to specific functions of an individual register. So for example, when we talked about the B register, there's this control pulse that we talked about, which is the RL10BB, and this means it only reads the low 10 bits of register B out onto the write lines, and that's because it's being used as kind of a memory address. There were kind of the Z15 and Z16 signals that we looked at as part of the Z register. But as we get into some of these other registers, like the A register and the L register, so the A is the accumulator and L is the low word part of the accumulator for double precision calculations, we're going to start to see additional functionality that's driven by various control pulses. So for example, we have this A2X pulse, which would enter, basically moves bits 16 through 1 of register A directly into register X. So it doesn't go along the write lines. It's not a kind of a typical, use the octal transceiver to push the contents of A onto the bus. This is a direct connection between A and X. So we'll have to, factor that in. And some of the other registers start getting, again, more complex with different functionality that they're going to have to require. So we've got this one, which is G2LS, which is enter bits 16 through 4 of register G into register X. This is for multiplication. So ZAP is actually related to multiplication functions and some of the shifts that are done in the registers to enable multiplication. But as we go through this, we need to not only look at the description of the register itself and the functionality that's described in the sections we've looked at, but we need to make sure that if there are any control pulses related to that particular register, that we're taking those into account as well. And so that'll be something that we'll start looking at more and more of as we go through some of the more complex registers and some of the functionality that's going to have to be enabled in order to replicate how it is that they work and what they provide to the functioning of the computer itself. Well, that's it for today's video on the Q register. As always, please subscribe if you want to see when new videos are coming out. I'm going to continue to try to post one video a week as we work through the project. As always, please send any comments, questions, feedback that you have. More than happy to answer questions or go into more areas that people have a particular interest. Anyways, thank you very much, and we'll see you next time.